high current electrode systems, inductive effects can indeed contribute to arcing phenomena. Here's a breakdown of the underlying principles. The fundamental concept to grasp is that when you have very high currents, like the 4000 amps resistive load specified or the 3000 amps mentioned during arcing, they generate strong magnetic fields. These magnetic fields are not static, they are dynamic and fluctuating, especially with alternating current systems. Now, consider a grounded metallic plate in proximity to these electrodes. The changing magnetic fields induce eddy currents within this plate. Eddy currents are circulating currents that flow within a conductor due to electromagnetic induction. These eddy currents, in turn, generate their own magnetic fields. The interaction between the magnetic fields produced by the electrodes and the magnetic fields created by the eddy currents in the metallic plate is where things get interesting. If the orientations of these magnetic fields align in a favorable manner, they can effectively create a path of lower reluctance. Reluctance in magnetic circuits is analogous to resistance in electrical circuits. It's the opposition to the establishment of a magnetic field. A path of low reluctance means that the magnetic field lines prefer to flow through that region. This concentration of magnetic flux can significantly influence the current distribution in the system. When a low reluctance path is established between one of the electrodes and the grounded plate, it concentrates the electric field in that region. This, coupled with the high current density already present, can lead to a phenomenon known as electrical breakdown of the air gap. Electrical breakdown occurs when the electric field strength exceeds the dielectric strength of the air, causing the air to become ionized and conductive. This ionization creates a conductive pathway through the air gap, resulting in an arc. The fact that arcing is observed from only one electrode and not the other suggests an asymmetry in the system. There could be several reasons for this. Firstly, there might be subtle differences in the geometry of the electrodes or their positioning relative to the grounded plate. These geometric variations can affect the distribution of the magnetic fields and, consequently, the locations where eddy currents are most intensely induced. Secondly, there might be unintended conductive paths or lack thereof influencing the current flow. Even if there are no direct conductive paths to the non-arcing electrode, subtle differences in impedance or capacitive coupling could play a role. Thirdly, consider the possibility of localized variations in the air gap distance. A slightly smaller air gap at one electrode compared to the other would make the smaller gap more susceptible to electrical breakdown. To further investigate and mitigate this arcing issue, consider the following aspects. Firstly, examine the electrode geometry. The shape, size, and surface finish of the electrodes can significantly influence the electric field distribution and the likelihood of arcing. Sharp edges or points on the electrodes tend to concentrate the electric field, increasing the risk of arcing. Ensuring that the electrodes are smooth and free of any sharp features can help to distribute the electric field more evenly. Secondly, scrutinize the gap size. The distance between the electrodes and the grounded plate is a critical factor in determining the breakdown voltage. A smaller gap requires a low voltage to initiate an arc. Precise control and maintenance of the air gap are essential. Thirdly, assess the surface conditions. The presence of contaminants such as dust, oil, or oxidation on the surfaces of the electrodes or the grounded plate can significantly reduce the dielectric strength of the air gap. Regular cleaning and maintenance of these surfaces are crucial to prevent arcing. Fourthly, address the magnetic field symmetry. Analyze the arrangement of the electrodes, the saturable core reactor, and any other nearby metallic components to identify potential sources of asymmetry in the magnetic field distribution. Adjustments to the positioning or shielding of these components may help to improve the symmetry and reduce the likelihood of arcing. Fifthly, incorporate ground fault detection. Given that the system is currently ungrounded and lacks ground fault detection, it is highly recommended to install a ground detection system. A ground fault detection system can quickly identify and alert operators to any unintended current leakage to ground. This allows for prompt intervention to prevent arcing and potential equipment damage. There are several types of ground fault detection systems available, each with its own advantages and disadvantages. One common type is a ground fault relay, which monitors the current flowing in the ground conductor and trips a circuit breaker if the current exceeds a predetermined threshold. Another type is a ground fault indicator, which provides a visual or audible indication of a ground fault. The specific type of ground fault detection system that is most appropriate will depend on the specific characteristics of the electrical system and the application. Sixthly, consider shielding and grounding. Implementing shielding measures can help to contain the magnetic fields and minimize the induction of eddy currents in the grounded plate. This can be achieved by enclosing the high current components in a conductive shield that is properly grounded. Proper grounding practices are also essential to ensure that any fault currents are safely diverted to ground. Seventhly, evaluate the saturable core reactor. The saturable core reactor is used to control the output current. The characteristics of this reactor, such as its inductance, saturation current, and response time, can influence the transient behavior of the system and potentially contribute to arcing. Carefully evaluate the reactor's performance and ensure that it is properly sized and configured for the application. Eighthly, analyze the system impedance. The overall impedance of the electrical system, including the transformer, electrodes, and connecting cables, can affect the magnitude and distribution of the current flow. A high impedance can limit the current and reduce the likelihood of arcing. Conversely, a low impedance can increase the current and make the system more susceptible to arcing. Ninthly, monitor for harmonics. The presence of harmonic currents in the electrical system can exacerbate arcing problems. Harmonic currents are currents that have frequencies that are multiples of the fundamental frequency of the system. These currents can cause overheating of equipment, increased losses, and voltage distortion. If harmonic currents are present, it may be necessary to install harmonic filters to mitigate their effects. Tenthly, verify insulation integrity. Ensure that the insulation on all electrical components, including the electrodes, cables, and transformer windings, is in good condition. Damaged or deteriorated insulation can provide a path for current leakage and increase the risk of arcing. Regularly inspect the insulation and replace any components that show signs of damage. 11th, review the grounding practices. Make sure that the metallic plate is properly grounded. A poor or inadequate ground connection can create a high impedance path for fault currents, increasing the risk of arcing. Confirm that the ground connection is secure and that the grounding conductor is of adequate size. 12th, investigate any nearby metallic objects. The presence of nearby metallic objects such as pipes, conduits, or equipment enclosures can influence the electromagnetic fields and potentially contribute to arcing. Ensure that these objects are properly grounded or shielded to minimize their impact on the system. 13th, consider using a different electrode material. The electrode material can affect the arcing characteristics. Materials with higher melting points and better arc resistance may be more suitable for high current applications. Evaluate the properties of different electrode materials and select the one that is best suited for the application. 14th, optimize the electrode cooling. Excessive electrode temperature can increase the risk of arcing. Implementing effective cooling measures, such as water cooling or forced air cooling, can help to keep the electrodes cool and reduce the likelihood of arcing. 15th, implement predictive maintenance. Regularly monitor the condition of the equipment and perform preventive maintenance to identify and address potential problems before they lead to arcing. This can include visual inspections, infrared thermography, and electrical testing. By implementing these recommendations, it is possible to significantly reduce the likelihood of arcing in high current electrode systems and improve the reliability and safety of the equipment. Remember that addressing arcing issues requires a comprehensive approach that considers all aspects of the electrical system, from the electrode geometry to the grounding practices. A careful analysis of the system and the implementation of appropriate mitigation measures can help to ensure safe and reliable operation. In the context of the given scenario, the 1850 kV single-phase transformer operating at a relatively low voltage range of 300 to 800 volts alternating current, yet carrying a substantial 4000 amps resistive load, emphasizes the criticality of managing the electromagnetic fields and current distribution. The presence of a saturable core reactor further complicates the analysis, as its nonlinear behavior can introduce harmonics and transient effects into the system. It is imperative to thoroughly evaluate the reactor's characteristics and ensure that it is properly coordinated with the rest of the electrical system. The fact that the electrodes penetrate a grounded metallic plate introduces a significant ground fault risk. Any insulation failure or arcing event can result in a large fault current flowing to ground. This underscores the importance of installing a ground detection system to quickly detect and respond to any ground faults. The observed arcing from only one electrode suggests a localized problem. It is essential to conduct a thorough inspection of the electrode, its connections, and its surrounding environment. Look for any signs of damage, contamination, or misalignment. Also, carefully measure the air gap distance between the electrode and the grounded plate to ensure that it is within the specified tolerance. This statement that there are no other direct conductive paths to the non-arcing electrode is a critical assumption. It is important to verify this assumption through thorough testing and inspection. Even seemingly insignificant conductive paths can have a significant impact on the current distribution and the likelihood of arcing. Given the high currents and voltages involved, safety should be the top priority. Ensure that all personnel working on or near the equipment are properly trained and equipped with appropriate personal protective equipment. Follow all applicable safety regulations and procedures. It is also recommended to consult with qualified electrical engineers and safety professionals to conduct a comprehensive risk assessment and develop appropriate mitigation measures. The use of a saturable core reactor to control the output current is a common practice in many high current applications. However, it is important to understand the limitations of this technology. Saturable core reactors can introduce harmonics into the system and can be susceptible to saturation effects. It is essential to carefully select and configure the reactor to minimize these issues. The relatively low voltage range of 300 to 800 volts alternating current, coupled with the high current of 4000 amps, results in a relatively low impedance system. This means that even small changes in impedance can have a significant impact on the current flow. It is essential to carefully control the impedance of the system to prevent excessive currents and arcing. The electrodes passing through a grounded metallic plate creates a high risk of ground faults. It is essential to install a ground detection system to quickly detect and respond to any ground faults. The lack of a ground detection system in the existing configuration is a significant safety hazard. The observed arcing from one electrode to the metallic plate suggests a localized problem with that electrode or its surrounding environment. It is essential to conduct a thorough inspection of the electrode, its connections, and its surrounding environment. The assumption that there are no other direct conductive paths to the non-arcing electrode must be verified through thorough testing and inspection. The high currents and voltages involved in this application require strict adherence to safety regulations and procedures. All personnel working on or near the equipment must be properly trained and equipped with appropriate personal protective equipment. The recommendation to consider installing a ground detection system is of paramount importance given the ungrounded nature of the transformer and the potential for arcing to the grounded metallic plate. Ground detection systems are designed to detect unintended passive current flow to ground, which can occur due to insulation failures, equipment malfunctions, or other unforeseen events. By detecting these ground faults early, the system can take corrective action to prevent more serious problems such as arcing, equipment damage, and electrical shock hazards. There are several types of ground detection systems available, each with its own advantages and disadvantages. One common type is a ground fault circuit interrupter, or GFCI, which is designed to quickly interrupt the circuit when a ground fault is detected. Another type is a ground fault relay, which is a more sophisticated device that can be programmed to detect different types of ground faults and to take different corrective actions. The specific type of ground detection system that is most appropriate will depend on the specific characteristics of the electrical system and the application. However, in general, it is recommended to use a ground detection system that is designed to detect both high impedance and low impedance ground faults. High impedance ground faults are those that occur when the path of current flow to ground has a high resistance, such as through a layer of dirt or moisture. Low impedance ground faults are those that occur when the path of current flow to ground has a low resistance, such as through a direct short circuit. Both types of ground faults can be dangerous, and it is important to detect and respond to them quickly. In addition to installing a ground detection system, it is also important to ensure that the electrical system is properly grounded. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to prevent voltage buildup and reduces the risk of electrical shock. The grounding system should be designed and installed in accordance with all applicable electrical codes and standards. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. Section 250.4 outlines the general requirements for grounding and bonding, while Section 250.20 specifies the types of systems that are required to be grounded. The NEC also provides requirements for the size and type of grounding conductors, as well as the methods for connecting grounding conductors to equipment and to the earth. In addition to the NEC, there may also be local electrical codes and standards that apply. It is important to consult with a qualified electrical engineer or contractor to ensure that the grounding system is designed and installed in accordance with all applicable requirements. Another important consideration is the maintenance of the electrical system. Regular inspections and testing can help to identify potential problems before they lead to arcing or other hazards. The insulation resistance of conductors and equipment should be tested periodically to ensure that it is within acceptable limits. The grounding system should also be inspected regularly to ensure that all connections are tight and that there are no signs of corrosion or damage. Any problems that are identified during inspections or testing should be corrected promptly. The electrodes, the air gap, and other areas in the electrical circuit need to be inspected. This will help ensure the reduction in the likelihood of arcing. The shape and position of the electrodes, the air gap distance between them and the metal plate, and the conditions of the electrode surfaces all affect arcing propensity. Proper spacing between the electrodes and the plate, as well as minimizing any conductive paths between the non-arcing electrode and the plate, can minimize the risk of arcing. And the installation of the ground detection system will help monitor for ground faults. Finally, be sure that the electrode geometry is inspected. The shape and position of the electrodes can influence magnetic field interactions and arcing behavior. The air gap distance between the electrodes and the metallic plate is critical. Also, the cleanliness and smoothness of the electrode and plate surfaces can affect arcing propensity.